Here we're going to look at the concept of electronegativity. It's probably one of the most important concepts in chemical bonding, so it's really important to get to grips with it early on. So it's the relative attraction that an atom has for the shared pair of electrons in a bond, or a covalent bond. We've just looked at covalent bonding. We know that covalent bonding is a sharing of a pair of electrons. If I consider that to be a pair of electrons between two arbitrary atoms, X and Y, we know that the electrons themselves will just fluctuate, or you just move between the two atoms. Okay, so both atoms have a pull on the electrons, and they pull on the electrons from the protons within the nucleus. But because all atoms are different, some atoms have a different pull on those electrons than others. So therefore we say they've got a higher electronegativity. We can think of these electrons in a slightly different way. If you think back to the atomic structure section, we know that electrons themselves can't be positioned or located at any one point in time. So we know they occupy these things called atomic orbitals. That's this one here. But we also know that when atoms share their electrons, those orbitals overlap. Sometimes you get very strong overlap, which is a sigma bond. It's a head-on overlap. Sometimes the overlap is slightly weaker. It's a side-on overlap, and you get what's known as a pi bond there. But I can represent them essentially like this. Where the atomic orbitals overlap, they form what's known as molecular orbitals. And you get a bonding orbital and an anti-bonding orbital. But we're not going to go into that in too much detail. For now, all you need to know is that the electrons occupy this region between the two atoms in the covalent bond. Now, if both atoms have an equal pull on those electrons, then the electrons are going to just fluctuate in between the two atoms here and here. Those electrons are constantly moving between the two atoms. But if one of the atoms has a stronger pull on the electrons, well, that electron density might shift closer to one of the atoms, okay, and therefore go away from one of the other atoms. And this is what we're going to look at now. So let's just say that this atom Y had a stronger pull on those electrons. Well, if it's got a stronger pull on those electrons, then the electron density will just get closer to it. And if the electron density starts to get closer to one of the atoms, then that atom itself builds up a partial negative charge. And if this atom then loses that electron density here, well, that starts to get a partial positive charge because it's losing some electron density. So we could end up with a situation where one of the atoms just pulls most of the electron density towards itself, okay? And then the other atom doesn't have much electron density around it. So this atom on the left here has a quite strongly partial positive charge, and this atom on the right has a quite strongly partial negative charge. So we create a system where there's an unequal sharing of that electron density because one atom has a greater tendency to pull it towards itself. Now if we have a look at the periodic table, and especially the log tables, there is actually a table of electronegativity. So here what we can see is that the atoms with the highest electronegativity are over on the right of the periodic table, while those with the lowest are generally over on the left, the metals here. Okay, so why would something over here attract the electrons towards itself more so than something on the left-hand side of the periodic table? Well, if something's going to attract a shared pair of electrons, then it's probably going to have quite a large number of protons. As we go across the period in the periodic table, the number of protons increases. Okay, well, if it's attracting the outer shell electron, then the electron that's going to be closest to the nucleus is the atom which has the fewest number of shells. So as you go across the periodic table towards the right hand side and up, you get the most electronegative atom, which is fluorine. So we know fluorine is the most electronegative. Hydrogen is moderate at 2.2, fairly low electronegativity. The metals are extremely low, they are electropositive. And carbon as well, there's not much difference between carbon and hydrogen. So if we were to look at what impact this has, well, it has a really big impact in terms of how molecules interact with other molecules. Because now we know that the charge density within a molecule isn't distributed evenly if you've got atoms with different electronegativity values. So if we take an example like hydrogen fluoride, I need to look at fluorine's electronegativity and I see it's 3.98. I look at hydrogen's, it's 2.2. So fluorine has got a much greater pull on the electrons. So fluorine will have a partial negative charge and hydrogen will have a partial positive charge. Okay, So what that does is it actually creates what's known as a permanent dipole within the molecule, like this, which just shows that one side of the molecule is more negative than the other, and that's what's known as a permanent dipole. So this has all sorts of implications in terms of chemical bonding and interactions between molecules, and we can look at electronegativity differences, and what it allows us to do is actually classify covalent bonds as being polar covalent or non-polar covalent. It also allows us to determine whether a bond tends towards being ionic in nature or covalent in nature. So if we just have a look on the right hand side, if the electronegativity difference between the two elements is less than 0.4, well, there's no real difference there. Neither atom has a stronger pull on the electrons, and you get a non-polar covalent bond. So carbon-hydrogen bonds, for example, are all non-polar covalent. Then, if we do get an appreciable difference in electronegativity between 0.4 and 1.7, then we have this red square here, we have a polar covalent bond. And if you get an electronegativity difference which is greater than 1.7, then the nature of the bond tends to go towards being more ionic. It doesn't mean you'll always get an ionic bond, but it tends to be more ionic in nature. So this is really, really important for how molecules interact, which is discussed in the intermolecular forces video next. So that's just to recap electronegativity. We look up the log tables, look at the electronegativity difference, which is just the pull that an atom has on the electrons. If it has a stronger pull on the electrons, therefore it's going to have a higher electronegativity, which means it is possible for that to have a permanent dipole within the molecule.